All right, so we've been talking about probability distributions, and we did some graphs with some histograms, and we described how they looked, and we talked about if they were symmetric or skewed left or skewed right. Well, normal distributions are distributions that have lots of cool qualities to them. So first off, they are perfectly symmetrical. So think about this if I fit lots of little bar graphs in here. It would be perfectly symmetrical like this, okay? In the middle, exactly in the middle, is what? That's the Greek letter mu. That means that is our mean. Okay, now your book, it's not a problem stats book, so it kind of, I don't want to go too far in depth. This can mean mean. It's the mean of a sample. Yes, X bar. And mu is a population mean. So the difference in population and sample, population is every single subject in whatever you're looking at. So if I was talking about doing a study on high school students, then every high school student in the world would be the population. The sample might mean that I use Camden High to represent the population, or I do a simple random sample of students around. And so finding the mean of the entire population can be quite difficult. So a lot of times we use the sample mean to represent the population, okay? Now this is not anything, I told you the book doesn't go too far in depth on a lot of this stuff. It doesn't, I would like for it to go a little further in depth than what it does, but they'll interchange those, and they're really not interchangeable, but they will. So just be able to recognize each one for what it is. Now, within this normal distribution, okay, I can classify some of the data here. I can say that as long as it's normally distributed, and the problem will say this data is normally distributed, 68% of all the data lies within one standard deviation from the mean. Uh-oh, we don't know what standard deviation is, right?
The mean is the middle.
The mean happens in the middle, that's the average, right? Standard deviation measures variance. It measures how spread out it is, okay? So standard deviation, if the whole thing had, think about like a range is a measure of variation, okay? Of how much it measures. If you take the high minus the low, it tells you how much it spreads out. Standard deviation kind of takes that range almost, and there's a complicated formula. Again, we're not going to get into that as to how we find the standard deviation, but it kind of takes the range of most of the numbers and divides it into chunks. So this tells us, and by the way, again, we can have S is standard deviation of a sample, standard, yeah. And sigma is standard deviation of a population. So if I go to the right, this would be the mean plus one standard deviation. It's a measure of variation. For instance, I might say the mean of, let's think, what could we look at? Yeah. Sigma. It's a Greek letter. It looks like that. It's like a 0 with a line on top.
So what does top mean though?
That's lowercase sigma.
What are you doing for top?
Population. Let me see what I think your book does. Yeah, that's what your book uses.
Yeah, what do you call the N?
Mu.
Say mean.
I don't know. What else called mu? Maybe it's different. I don't know.
I thought Americans.
That's the way I was always taught was mu. She's Greek.
She's American though.
I was taught it as mu.
Yeah. All right.
Like MUSU.
I didn't mention this up here, but I hope it stands. It stands to be, yeah. I hope you can look at that and tell that's a symmetric distribution. And with symmetric, this is a perfectly symmetrical distribution, which means it's exactly the same on either side. All right, so 68% of all of my data falls within one standard deviation of the mean. Yeah. Standard deviation of the population.
All of these.
Can I just catch up real quick?
Okay, let's give me a break.
What does what mean? It's a measure of the variance, how much the data varies.
Can you write down?
Yeah. Standard deviation of population. I ran out of room.
So standard deviation.
All right, I know this is a lot throwing at you. Remember, this is kind of a quick overview of some pretty important problem stats concepts. What this means, if 68% lies within one standard deviation, then there's a 68%, the probability is 68% that you randomly choose one and it falls in this area here, okay? Now, for instance, if I told you that I had a certain set of data, let's say I want to look at the number of Christmas presents teenagers get. And so, and let's say in Camden, let's say the population is Camden, let's just say, what's the average? Yeah. Oh, yeah, sorry. I want to know, I'm going to do a study on how many gifts the average kid gets between the ages of birth and 18 in Camden. So I would randomly pick, and so let's say after we did all this big study, we found that the average number of presents, and remember X bar and mu is the same thing, is 5. Let's go more than that. Let's go a little more than that. Let's go 12. Let's say that the standard deviation is 2. Okay. That means that 68% of students, or of kids between birth and 18,
How would you know this? Oh, okay.
yeah, received between 10 and 14 presents.
Wait.
Because 68% of all my data falls within one standard deviation either way, hush, Shamik, of the mean. Does that make sense? Yes, or 0.68.
It's always 0.68.
Now, because it is symmetrical, not only is this 68%, but this is 34, and this is 34, because it is symmetrical. Okay? So then I could go a step further, and I could say, well, 34% of the kids in Camden received between 12 and 14 presents. Does that make sense what I'm saying to you?
So is mu the same as X
Yeah, X bar, yes.
bar? Okay.
Okay. Now, we go out another standard deviation away. This one is mu plus 2 standard deviations. Oop, and this one's mu minus.
Don't have it.
Can I just write an M?
95% of all the data falls within 2 standard deviations away. Now think about this with me for just a minute. If it's symmetrical, and between the yellow lines is 95%, but between the white lines is 68%, how much is each little yellow piece? All the white is 68%.
And then we subtract 95.
Mhm.
27%.
27. So half of that, because I got two of them, 13.5. We're going to go out one more.
I can't put it down.
It's very important that you can fit everything. If you need to go to another page and rewrite it, this is called the empirical rule. These are what I call magic numbers. But there's one more level we need to take it to. And that is 3 standard deviations out. And 3 standard deviations out holds 99.7% of the data. Notice it's not 100%. Okay. So what are these little pieces? You're close. I think it's like 3.25 or no, 2.35. 2.35%. Now remember, if I were writing this as a decimal, it would be 0.0235. Now somebody made a good point because they said it's not 100%, and it's not. Because I've got this little bit left over here in the tails. That little bit left over should account for 0.3%, right? Yeah. But I got to split it in 2. Now together, that should make 100%. If you noticed how we derived this, finding each little piece as we went, it's pretty easy to come up with if you remember these 3 numbers. I call those 3 numbers magic numbers. 68, 95, and 99.7. They call this the empirical rule. That if you have a normal distribution, your data will fall between standard deviations in this way. It's the empirical rule. I just call them magic numbers because they make life easy. So let's do a couple examples and kind of interpret this.
Hey, I just got that thing.
The square?
So will this always stay the same?
This is always the case for every normally distributed. All right, so keep this as a reference. I'm gonna keep coming over to it. But let's do, for example, a normal distribution has a mean X bar and a standard deviation of sigma. For a I'm reading it the way it's going to be set up in your. Well, I want to set it up. This is what I was saying. It is not proper statistics to mix sample and population, but your book does it. And I just felt like I needed to tell you that that wasn't proper without. All right, so mu and X bar are still means, okay? It's a normally distributed. I want to know what's the probability that X falls between 2 standard deviations to the left and the mean. All right, now look. Don't make this harder than it is. Look at it for a minute. This is an inequality. I'm talking about the probability of randomly selecting some value. Okay? So if I scroll over, okay, first thing I'm going to look for is 2 standard deviations to the left. That occurs here in yellow. So I'm right here.
Are those numbers
Look.
always the same?
No. Yes, the ones that are on there in yellow. No. Yes.
34%.
Yes. This is the yellow line on your standard normal distribution. Remember, you start with mean, and I'll do it as x bar so you're not quite as confused. Minus sigma, minus 2 sigma, minus 3 sigma, plus 1, plus 2, and plus 3. It says, what's the probability that you randomly pick an x and it falls between here and here? Well, all you have to do is look between those two. What's the percentage there? Between those two, what's the percentage? 34 and 13.5, which is 47.5.
Wait.
Is that the answer?
Wait.
You're just adding those two percentages together. Absolutely.
Why is that?
Because that's what it asked me. It said it's normally distributed. It said what's the probability that it falls between there and there. Let's put some numbers in it and see if it makes a little more sense. Shh, guys. 47 is coming because I added together minus 2 in the middle. Those two columns I added together. This thing is not wanting to move with me today. What if I told you the score on an entrance exam for a firefighter program, the scores are normally distributed with a mean of 200 and a standard deviation of 20. First of all, I want you to tell me what percentage score below 160. So my question is 160, is it occurring on like a magic number? In other words, is it an even number of standard deviations away? Sure. If the middle happens at 200,
The middle is going to be, oh, that's,
one standard deviation away is 220, 2 is 240, and 3 is 260. If I go backwards on it, I have 180, 160, and 140. Do you all agree with that?
Yes.
I want to know the percentage that score below 160.
so from The 200 to 160. Oh, so 160.
Below 160. So what percentage would score below 160? So understand that's 2 standard deviations to the left, right? So if I go back to my chart, come on, 2 standard deviations away, so from here over, so 2.35 plus 0.15, right? It's everything to the left, which would be 2.5%. If it's magic numbers are easy as long as they happen. Whenever I say magic numbers, I'm really talking about that they occur an even number of standard deviations away. Does that make sense? Nope. So because this was 2.35 and this was 0.15, then we said we add them together to get the 2.5%. That makes sense.
That's all we learned today?
So that occurs when it's an even number of standard deviations away. Easy peasy, right? That's what I had intended to do with you yesterday and save the chart for today, but we're going to just do it all today. The question occurs with what happens if I looked at this same problem with this same mean, and I said, I don't want to know what percentage scored below 160. I want to know what percentage scored below 170. So now I have a problem. Because it's no longer a magic number. This does not happen an even number of standard deviations away. Yes. 2.35. So what happens if it's not a magic number? Well, that's when we have to convert it. We convert to what we call a Z-score. Okay? To convert to a Z-score, we take our X.
So X is going to be Z in this case?
Well, we're converting it. We subtract the mean, or the mu is what it should be, and divide it by the standard deviation. So in our example earlier, what was the mean? 200. Standard deviation was 20. So I wanted to know less than 170. So because that doesn't occur at 220, 240, 260, or 180, 160, 140, I have to convert it. So watch what happens when I convert. 170 minus 200 divided by 20. You need to always round it out 2 decimal places. Negative 30 over 20. Negative 1.50. Do we all agree? This is the only little formula you have to memorize. Take out your table that I gave you. If you noticed, one side is positive, one side is negative.
Yeah.
All right. Obviously, I'm on the negative side, right? Because my score is negative. The first column, the way it's set up, and students always have a hard time reading this. I've never really understood. You've got a Z in the corner. Here you've got a number. That's what we just found was a Z. And up here, we've got some decimals. Okay? This column, this first column, that's your ones and your tenths place. This column up here is your hundredths place. So you're going to just match up. If you look at my number, my ones and tenths are negative 1.5. My hundredths are 0. So look at your chart and tell me what you think the corresponding value is on your chart for negative 1.50. Yes.
How would you find
Look at your chart,
that?
go to negative 1.5,
Okay.
and then go over to the 0.00 column. Okay? Now let me interpret what this means for you. This means if I took that same curve here, right? Here was my mean. This 170 happened over here. It wasn't at a standard deviation. It actually, the z-score is actually the number of standard deviations away that it happened. You're converting it over to the number of standard deviations. It happened 1.5 standard deviations left. Okay? So what that means is at this point, so this is mu minus 1.5 standard deviations.
Why? That's not what it is.
Yeah, that was our z-score. The z-score, when you look it up, tells you that this area that's shaded is 0.0668 or 6.68%. Does that make sense? A little bit? See if it makes sense. Where? Minus 1.5 sigma. Notice at the top, there's a little curve and it's shaded a certain way. That's telling you that it's giving you the area to the left. So what if I wanted the area to the right?
You'll be positive.
Like what if I wanted to know how many scored greater than or equal to 170? How many does a distribution, what's the total area of a distribution? 100% or 1, right? Well, because this is shading to the left, what would the yellow area be? Somebody with a calculator.
It would be 1 minus 0.006.
Oh, not a good lesson to zone out on. What's it give you?
So we're doing 1 minus,
0.0668.
it's 0.9334.
So 90,
It's
huh?
2.
92%? No, what? What's 2?
0.932.
Ah! Okay. So 6.68% of people scored below a 170, which means that 93.32% scored above a 170. Does that make sense?
Yeah.
So the question's going to become as you look at your homework, because I'm not going to tell you whether or not it's magic numbers. Is can I use a magic number? Do I not use a magic number? So let's do another one. Y'all ready?
Wait, so why'd you go over to the 0.00?
On Norbert though?
Which 0.00?
That's what I'm confused about.
Yeah, on the table.
Yeah, I just looked at why then.
Because this gives me my hundredths, and I went to the hundredths column of 0.
Why?
Because that's the number, 1.50.
But so this is 0 and 100. Gotcha.
Tell me this while I get your next problem. Give me the z-score, or give me the value that corresponds to the z-score of 1.17. Positive 1.17.
Oh, positive.
Yes. Everybody find it. Make sure you find it.
What?
You said Grant?
Look at it. Look at it. Make sure you can find it.
At what?
1.17. 1.17 on your table. Flip it over for the positives.
It's only 1.7.
No, 1.17.
Oh. They got a 1.
So go to 1.1 and then go over till you get to 0.07.
8
8790. Does everybody see
Yeah,
that?
that's-
How about 2.63?
2.6.
Point 995.
9957.
Notice something. The even numbers are still on here. You still have 1, 2, and 3. Anything above, I think, 3.5, you consider close enough to 100% to round it. So go to, like, if I wanted 1.23, go to 1.2, and then go over until you get to 0.03. Okay.
It's in the back.
Let's do this one together. The blood cholesterol readings for a group of women are normally distributed with a mean of, and I'm going to switch over to X bar since that's what your book uses, 172 and a standard deviation of 14. What percentage of women have scores between 158 and 186? See if you can do this one on your own. Is it on the chart? I don't know.
Nah, I think I'm doing the thing with the picture.
Why did you do 172?
That's the mean. Anybody got it yet? 68%. Both of those are one standard deviation away.
It's just like, it's always gonna be 68 if it's one single deviation.
As long as it's one in each direction, yes. Ooh,
Oh, I got it.
not a magic number, right? Do we see that it's not a magic number, and do you see why?
He says it's odd though.
Hmm?
He says it's odd, it ain't a magic number.
What?
Man,
What are you gonna have to do if it's not a magic number?
a little formula jump. Ain't it?
Z-score.
Yeah, that's a-
What's the difference between X and X equal 100?
What'd y'all get for the Z-score?
Where did you get the 190 from?
This is a separate problem. What'd you get? 0.8997, so I'm gonna have to round that to 0.90.
So it's the same thing, but not the same equation.
Right. It's because if you look at this line, 190 happens about right here. That's not on one of my standard deviations. All right, so here's what, and I tell students a lot of times, I used to make everybody draw a curve and shade so you would actually see, so if it helps you. When I look at this, Here's my mean. 190 is about right here, and I'm asking for greater than, right? When you look up the z-score for 0.90, look at the top first. Which way is it shading? Look at the top of your z-score sheet. Which way is that curve shading? To the left. I need it to shade to the right. So in order to get that, I'm going to have to take the value in the table and do what with it? Change it how? Not to make it negative. Subtract it from 100%. Exactly. Or from 1 in this case in some decimals. So look up 0.9. 0.90. What do you get? 0.8159. The problem is 0.8159 is all of this area. That's not the area I want. I want that little white area. So to get that, I have to say 1 minus 0.8159. 0.1841. 18.4% scored greater than 190.
We are talking about.
Oh no, y'all. Oh no. That's the wrong z-score.
Oh.
I didn't double check behind y'all. What does the z-score, what's the z-score come out to be? 1.29. I don't know.
I said 1.29, so it's right.
1.29, which means that's what I'm looking up. All right, so look up 1.29. That's okay. What do y'all get? 9015. Which means now the white area is 1 minus 9015. Which is, give it to me, Juliana. 9.85% scored greater than or equal to 190.
How much?
9.85%. I'm going to do one more using these numbers, these same numbers. I'm going to make this one a little bit more difficult. Y'all ready? Because this one's going to be a little bit harder. I'm going to let you struggle through this one a little bit on your own first, and then I'm going to do it with you. I want to know what percentage scored between 146 and 204. And it's still very helpful if you set up your curve so that you know around where I'm somewhere here and I'm somewhere here, and I want to know the in-between. So you're really going to have to think on this one. So I'll give you a second. I'm going to pause it. You got to use the formula twice because you need it at 204 and you need it at 146. The problem is when you look up this z-score, it's going to give you from here all the way over to the left. So I'm basically getting all of that. When I look up 146, I'm getting all of this. So to find the green that's left, I would have to take the white and subtract out the yellow. So let's work on z-scores first. Okay.
are round.
What was my mean? 14?
You are round.
I mean standard deviation.
You are round.
Yeah, you're gonna have to.
We're still continuing on the last one.
Uh-huh. Using those same value. Oh no. I'm a dummy. Shamik.
Yo, oh, this is recording. Okay, well, y'all want to video on YouTube. I'm all smart.
I'm kind of working it out as you work it out so you can look up and check what you're doing.
Maybe we subtract that, right?
890. Everybody get those two numbers?
Why did you have one? Oh, the one blank.
When I looked up negative 1.86. They're switched around. I accidentally did the 204 first.
How'd you get .0314?
You subtracted that, you know?
Mm-hmm. I hope you all got 95.76%. If you didn't, where did you mess up? What happened?
146 minus
Not the front, it's like
114.
2957.
I got
Negative 1.785.
Oh, that's where you messed up.
So and then,
No, it's a Z-score. Your Z-score's off. 140, it's not 140, it's 146.
Oh, I didn't know why. How do you?
Yeah, I did that.
What is?
You did 140, hold on just a second.
Kelly, hear my.
Where does it keep going? 146 minus 172.
Oh, never mind. I got negative 25 over 14. Yeah, it's
All right,
negative
listen.
26.
Listen, let me give you something in general. And I'm hesitant to tell you this because different Z-score tables do different ways. Some of them shade left, some of them will shade right. Okay, so you really have to check. That's why they have it shaded at the top like that. All right, so you need to check. But in general, if you're finding greater than something, you're going to have to subtract this number from 1. If you're finding less than something, this number will work. If you're finding between two numbers, you're going to have to subtract those values. Does that make sense? So check the way you're shading. All right, let me give you homework.